Uh, okay, hello everyone. Last speaker this morning is Professor Yongquan Hu from Chinese Academy of Science, and he will talk about multivariable phi gamma module and local global compatibility. Let's welcome.
Okay, thank you for the introduction and also for invitation to speak here. I will talk about some recent joint work with Christophe Breuil, Florian Herzig, Stefano Morra, and Morra and Schraen. So the object is called the mathp long-length program. Let me give you some introduction. So for p prime number and n natural number n and k a finite extension of qp, we search for a correspondence between on the left-hand side mod p representations, Galois representations, rho bar of the absolute Galois group of k. On the right-hand side, we take admissible smooth still mod p representations of GLN of k. We only know very few cases. In the case n equals 1 follows from class field theory. For the case of GLQP, this is work of many people, Breuil, Colmez, Kaysen, and Pascunas. In this talk, we will focus on the case n equals 2, and k is an unramified extension of qp. So f, small f, is the degree of the extension. So in the case of GLQP, there are two main results, very important results. So first one is due to Colmez. He constructed a functor from mod p representations of GL2QP. Here I should take admissible ones, and finite length goes to Galois representations. So his construction goes via the so-called phi gamma modules. It's well known that there's an equivalence between the category of phi gamma modules and Galois representations, proved by Fontaine about more than 30 years ago. So actually, Colmez constructed a functor from GL2QP representation to phi gamma modules. We will talk about it later. And another important result is that, so M to improve some, he called local global compatibility. Namely, he takes the etale cohomology of the modular curves with mod p coefficients. So from now on, I will take f to be a large finite extension of fp, to replace fp bar. This is harmless to do so. And we take the inductive limit for all n. So this space carries a continuous action of the Galois group of Q and also GL2 of AF. So AF is the finite adels of Q. You also take two-dimensional representation, continuous representations of GQ, which is irreducible and odd. With some minor restrictions, M to improve that when you take the home space from R bar to this space H1, the GQ representation, it can decompose as a restricted tensor product of some pi R bar restricted to GQL. So here, each pi R bar GQL is given by the mod p local long-length correspondence. So when L is not equal to P, this is due to work of Vinaya-Haas and Emerton. And when L equals P, it's just the one, constructed by Colmez, and of course based on results of Breuil. So let's pass to the GL2K case. To show that the functor of Colmez has good properties, one needs classification results of Bardet-Livni and also Breuil on multi-permutations of J2QP. But however, if K is not QP, we don't have such a classification, especially the supersingular permutations. By definition, these are the permutations not coming from parabolic induction. So these permutations are more complicated. We have several works on these permutations, knowing results, but all of these results are negative results. So Hamilton's local global compatibility motivates the following global construction of a candidate for the correspondence. So let's start with a local Galois permutation, two-dimensional rho bar. We can first globalize it to this R bar. So here F is a totally real field, such that for some place above P, the completion at V gives the local field F, and the restriction of R bar to GK is just the starting Galois permutation rho bar. Then you can cut out GL2K permutation. We denoted by pi rho bar in the cohomology of Shimura curves. Actually, it's tower of Shimura curves. Just similar to the results of Hamilton for modular curves. So for this, we need to choose some indefinite quaternion algebra D over F, which splits at V. So a priori, such a representation pi rho bar may depend on all the choices of global setting, like the field F and the global representation R bar or the quaternion algebra D. But some people believe that, like including me and including all our joiner others, we believe that this representation is independent of the choices. And also some others don't believe that. So the goal of this talk, the first thing is that we generalize the Colmez function to the J2K case. Yeah. It's in a sense admissible, not all the representations, but a class of admissible smooth representation of J2K to some multivariable phi OK cross module over some ring A. And the second thing is that we construct another functor from the Galois representation to also to the same category, etale phi OK cross module over A. Unlike the case of Fontaine in classical phi gamma modules, this is not what we constructed. This is not an equivalence of categories. And the main theorem says that such a diagram commute. You start from rho bar, and the above global method gives you some pi rho bar, which is a representation of J2K. And you can apply dA, the first functor, to get a multivariable phi OK cross module. And by the second construction, you get you get another again multivariable phi gamma modules after this from the dA tensor, and they coincide. Okay, for rho bar semi-simple and generic. So generic is a technical condition, and I will not precise it here. I think this. So the second functor is constructed in a purely local way. So we do get, although pi rho bar is obtained by global method, but it's associated multivariable phi OK cross module is local. So we do get some locality. Although this is not enough to show pi rho bar itself is local. So let me first pass through the construction of the first functor. I first recall the classical phi gamma modules. So in this talk, I just write phi ZP cross modules. This is introduced by Fontaine. We have such a phi-zp module over this low-Hom power series ring Ft. On T, we have the action of phi and gamma, and the two actions commute. It is called etale if you have such an isomorphism. The observation of Colmez is that when you have a G2QP representation, you can restrict it to the, it's called the P+. It's a monoid in G2QP. So here we take, be careful that this is a ZP minus 0. It's not a ZP cross. So it includes P in particular here. So he can translate the action of a P+ to a structure of a phi-zp modules by this dictionary. So you look at this completed group algebra, also called Iwasawa algebra. It is isomorphic to Ft, power series ring. And the action of this matrix and that one will correspond to the action of P and ZP cross. So Colmez, some precise definition is that you take an admissible representation of G2QP, and also it should take some finite length. And he takes a suitable subspace I plus pi inside pi. So this is stable on the P+, the monoid, and also such that the invariant subspace under this unipotent subgroup, 1ZP01, has finite dimensional. So why we require this one? This to make that when you take the Pontryagin dual, so this means Pontryagin dual. Also in this case, it's a linear dual. So this is a finitely generated over this Ft, over this ring. So when you pass change to the low-Hom power series ring, you get some finite dimensional phi gamma modules. Yeah, you get some. So this is important to get some finiteness of d of pi. If you just take pi itself here, and the invariant subspace by 1ZP01 has infinite dimension, you'll get some trouble. So we will come back to this point when you try to generalize this functor. You will really encounter this difficult for the finiteness. And the theorem said that d pi has finite dimension over Ft, and as I explained, it follows from this finiteness. And also this is an exact function. The proof of this exactness is a little bit complicated because when you pass from pi to I plus pi, this is not exact. So this is a little bit, complicated, but this part is not exact, but when you change the Ft, you will kill something, and to make this D to be exact again. So anyway, this is a G2QP case. So then next I will pass to G2K case. So I first introduce the ring A, which will be the base ring for our multivariable phi OK cross module. So I take N0 to be this unipotent subgroup, 1 OK 0 1. So and look at the Iwasawa algebra. So it is isomorphic to a power series ring with echo variables. Here we can choose the variables a little bit careful in this way. So you define this for each I from 0 to f minus 1, we define such a spatial element inside this algebra. And you can show these elements generate the maximum ideal, and they can generate the whole algebra. You have the natural Mn0 article filtration. So Mn0 is just the maximum ideal of this local ring. And let S to be the multiplicative set defined in this way. And for A, we first take the localization at A for this Iwasawa algebra, and then take completion. So the localization also has a natural filtration induced by this M0 RG once, and you take the completion for this filtration. So we get a complete filtered ring. And the phi OK cross action on Fn0 is the same as the J2QP case. It's by the multiplication inside the matrix, for matrix, in this way. And these two actions can extend to A by continuity. So for example, we have the phi action on the variable y0 is just yi minus 1p. So this is already here we see some difference. I mean, if you have only one variable, you get a phi y equals y to the power p. But now we have multivariable, so it does not send yi to yi to the power p, but you shift degree by one. You shift by one. Okay, so one case QP, we recover the classical ring FT. Yeah, we only have y0. Yeah, just a y0 to the p. Yeah, but I said yeah, in the classical setting. So yeah, and in the classical setting, when you localize, it's already complete. You don't need to complete again. So the construction of a dA, the first functor. So we start with pi. You can still have I plus pi, yeah, in the setting. But in this case, the invariant subspace has infinite dimension if you take pi to be a supersingular. It's always infinite dimension. And it's a result of Morra and Schraen, and later on generalized by his student Yongquan Hu. So even you, in the classical setting, we need to do some base change to FT, low series ring. So now, if you even you base change to, you take dual and you base change to the ring A, it's not clear to me. You can get some finite dimension things. So anyway, so our definition is as follows. We don't take I plus pi here. We take a pi, the whole pi, and its Pontryagin dual. Then it is a Fn0 module, and we base change to A, tensor with A. Then you take completion. Okay, then you completion. It's the same as that pi dual you localize at the multiplicative state, and then you complete. So here it's important that we give pi dual the MI1 arctic filtration. So here I1 is I didn't recall, sorry. I1 is a proper Iwahori subgroup. Means that when you mod P, it's an upper triangular subgroup. So MI1 is the maximal ideal of this Iwasawa algebra. It's important that we so first thing we take the MI1 arctic filtration on this pi dual, and then we complete. So the reason is that if you have A is a complete filtered ring, and M is a complete with a separated filtration, filtered module, then so M is finitely generated over A if and only if the graded module is finitely generated over the graded ring A. So this is a very easy fact, but will be crucial for later on to prove the finiteness of DL pi. So now I let C to be the subcategory of admissible smooth pi, satisfying this equivalent condition with M equals to pi dual S, with M to be that. Yeah, sorry, I should be the complete, should be a completion, okay. Should complete it. Anyway. So the theorem says that if pi is an object in the subcategory C, then dA pi is finite generally over O. And actually it's finite free. So this is essentially follow from the definition, okay? Although we don't know how large the category C is. And you can show that in general, if you have finite generality module over A, I mean, because you have a OK cross action on this module, you can show that it's actually free module. You can give on this dA of pi an action of phi and OK cross, but it's not obvious that it is etale module. But we can show dA of pi has the largest etale quotient, which is denoted by dA pi etale. Yeah, itself need not be etale, but you can always pass to get a etale quotient. And we can show if this is non-zero, then the etale quotient is also non-zero. Yeah. And third thing is that this is an exact function on the subcategory C. And this is clear in our setting because what you do is that starting from pi, you take Pontryagin dual, which is exact. And when you change to A, I mean, it's just to do some localization. I mean, okay, if you do some localization, it's also exact. And when you pass to completion, also exact. So everything is exact. You get exact function. So advantage compared to Colmez construction is that we don't pass through this I plus pi. But on the other hand, you need to handle the finiteness. So this is a completion thing. This step solves the finiteness. So now if we would like to know that how large this category is, okay? The important thing is that we can prove for the, if you start with rho bar, say generic, we have constructed some global, some representation of L2K by global method, this pi rho bar. We can show that this, all this pi rho bar lies in the category C. So roughly, I mean, actually this proof already appeared in the talk of Florian and Herzig last week. So roughly that we can compute, we can control the graded module of pi rho bar dual. We can control this graded module. It is cued by some ideal J, and such that this quotient is very simple in a very explicit and simple form. And so when you, let's say, when you localize at S, you look at the graded module, means that you need to localize at all the yi. You just get that this graded module localized at yi, inverting yi, this is a finite generative. Okay, I mean, it's easy to see that once you can show this graded module is cued by J. So so we know that now we know that all this representation coming from multiple cohomology lies in the category C. So we can talk about its associated multivariable phi OK cross modules over A. Let me remark finally that historically we first prove this second theorem for our theorem on to control the so-called Gelf on the Kirchhoff dimension of pi rho bar. And we realize this phenomenon for the graded module. And then we find the correct definition of this generalize the Colmez function and the ring A. Okay, this part is to explain that why taking MI1 article filtration and then taking completion is crucial for the construction. Let's take a very simple representation. Let's say Steinberg representation of a J2QP. So this representation, we know explicitly its structure. So if you look at its restriction to this unipotent subgroup, 1 DP01, it's just isomorphic to this means that locally constant functions are on QP with compact support. Okay, this group acts naturally on this space. So this is just the restriction of pi. And using that, you can see that pi dual is a free FT module of infinite rank. Yeah, because this one, I mean, this is injective 1ZP01 module. So when you pass into dual, you get some projective module, and equivalent is some free module. So if you base chain to FT, the Laurent series ring, you still get some infinite dimension things. Okay? So that's why, so even in this J2QP case, in the construction of a Colmez, here you need to take some subspace, which I denoted by I plus pi. Otherwise, you don't get finite dimensional modules. But let's compare with our definition. So if you compute the gradient module with respect to the MI1 article filtration, it's quite simple. Because f equals 1, you only have two variables, yz and mod by y times z. And when you localize at y, I mean inverting y, it is just free over the gradient module of this Laurent series ring, okay, even of rank 1. Okay, it implies that our version of d pi has dimension 1 over this ring, over this Laurent series ring. In other words, so the difference is that when you're taking completion, it kills a lot of unnecessary things. Yeah. Okay, now I explain briefly how to compute this dA of pi over. So we can talk about, I mean, it's because this thing lies in the category C, so we can talk about this multivariable module. Okay. It's hard to compute it directly because in the definition, you need first to pass to the Pontryagin dual of this pi. So usually Pontryagin dual is hard to handle. So the idea is that we compute it's a dual module. Okay. In some sense that we start with pi, we dual it to Pontryagin dual, and now for the module we dual again. Roughly, we pass back, we come back to the representation pi itself. So it's divided into several steps. So first of all, we construct a map from the ring A to the field F. It satisfies some property, but I will not precise that here. The psi A is some operator psi on A. It's some so it's the left inverse of phi of phi on A. So it satisfies something property like that. So if you take f equals 1, then you get I mean here you just get mu itself. So mu will induce I mean, naturally some map from home A, dA pi to A, I mean, this is A dual, okay, to this home continuous F linear morphism from dA pi to F. So this is, you can show this is embedded. So I mean, then you can check roughly by definition that the second space, okay, elements here all have the form xk. I mean, a series of elements in pi for all k bigger than or equal to 0. So roughly, as I explained at the beginning, when you taking, roughly we take dual twice to get back the representation pi. In the case of psi A is operate on A, some inverse of a phi. You also have that. Okay. And in the case of QP, just QP, I mean, if a case QP, this is just the isomorphism. Okay, this is explained in the paper of Colmez. And then we try to construct some precise elements inside here. Okay, for each tau in W rho bar denotes some cell weight. We can define a special element x tau by, I will give you example in next page to how to define such elements as a series of, a sequence of elements in pi, in this one. And we prove that x tau actually comes from this subspace, okay, this dual module. Okay. This is important because we need to compute that, right? We first construct elements here and show they actually comes from the image, the left-hand side induced by mu. In the case k equals qp, this is just isomorphism, so you don't need this step at all. Okay, but in general, this is not trivial. Not trivial step. It's quite it's very subtle to prove this x tau actually descends to this subspace, submodule. And then we show this explicit element from a basis of the dual module. And we explicitly compute the phi action and the OK cross action. The result, it turns out that this module has rank 2 to the power f and is already adile. Means that we don't need to take the adile quotient. It's itself already adile. Okay. Let me remark that during the computation or during the construction of this basis x tau, we only use very partial information of pi rho bar to compute the model. Yeah. Even so far, we don't have a complete understanding of pi rho bar. So we only have some partial ones. But still, they are enough to compute its associated multivariable phi OK cross module. You can ask if you can. Can you recover the pi rho bar restricted to the Breuil subgroup from this multivariable module? This is true. If k is qp, you start from pi. Start from pi. You compute its phi gamma modules, and then you have some way to recover pi restricted to Breuil. But now in our case, we don't know how to do it. Well, but still, it will be some mystery because this multivariable modules only uses some very partial information on pi rho bar, and if you can recover it, would be some mystery here. Yeah. Well, let's look at one example to how the computation goes on. We still have Sternberg representation, but now we can allow k to be general, not necessarily qp. So we take a non-zero vector in the I1 invariant. So I1 is a property Varphi, and it's knowing that this is invariant subspace is one-dimensional. Okay. So this vector satisfies some relations. So here on the line y means denotes this product of y0 to yf minus 1. So you can check that if you apply this matrix Pn001 to V and use y to the power p to the power n minus 1, you get back V. Okay, it's just a simple, computation, because we know the precise structure of this Steinberg. Now let's see how to define a sequence of elements in pi. So any k, you choose p to the power n large enough, so bigger than k. You set xk to the y p n minus 1 minus k of this expression. For example, if k is 0, okay, you just get V back. Okay. So it's a sequence of elements. For x0, it's just the starting V. For x1, x2, they satisfy this relation. Okay. It's more or less like you have roughly like you have V is x0, and you have V1, x1, x2 here. All these are linked by y. So the sequence of elements gives an element inside here. Yeah. And you can compute the action of phi. So here P roughly is a P001. You can check this relation. And similarly, you can check the action of OK cross. Yeah. This is, in general, for general pi rho bar, the computation is more complicated, but we do in this way to roughly following this strategy. Yeah, it's rather combinatoric. Okay. Now I talk the relation from the multivariable phi OK modules to the classical phi gamma modules or phi ZP cross modules. So you have a trace map from OK to ZP. It will induce the remorphism between the two Iwasawa algebras. Okay. And then you localize at S and complete, you get a map from A to FT. Okay. We still denote it by trace map. So you can look at the base change to this FT, okay, for these multivariable modules. The theorem says that the phi ZP cross module corresponds to some tensor induction of rho bar. So here, starting from rho bar argumentation of GK, you can look at the tensor induction. It's not the Euro induction, but it's called tensor. So the dimension of this representation equals to the dimension of rho bar to the power f, because GK is of index f inside the GQP. Okay. This remark tells you some structure about the phi ZP cross modules and also the phi OK cross multivariable modules structure roughly. For example, for this classical phi ZP cross module associated to the tensor induction, you can show it looks like a tensor product for all the embeddings from FQ to F. And here each d sigma rho bar is a phi to the power f ZP cross module over FT. And while for dA pi rho bar, it also decomposes the tensor product over all the embeddings of dA sigma rho bar. Here dA sigma rho bar is some phi f OK cross module over A. And each component, when you take trace map, it lifts d sigma rho bar here. So compatible with the left-hand side bed change things. Okay. So the third part is about the construction of the second functor. So unlike a Fontaine's theory of phi ZP cross modules, the category of etale phi multivariable phi OK cross module of A is not equivalent to Galois augmentations. At least we don't know. So the question is that how to relate rho bar to this dA par bar, okay, to these multivariable modules. So we need a looping tight phi OK cross module associated to some looping tight extension K infinity over K with the Galois group. So this looping tight extension has Galois group isomorphic to OK cross. Let's recall something about looping tight phi OK cross module. So we start with rho bar. So here rho bar can be of arbitrary dimension, not necessarily two-dimensional. So it gives an etale looping tight phi OK cross module. We denote it by DLT rho bar. It is over the ring. Is F times FQTK. So TK is some variable, analog to the T in QP case. So the phi action on TK is just it sends TK to TK to the power P. And if you have an element in OK cross, it sends TK to some ALTTK. So ATK, you can imagine, in the, I should take multiple reduction actually. In the cyclotomic case, it's just 1 plus T to the power P minus 1. 1 plus T to the power A minus 1, sorry. It's some analog to the cyclotomic polynomial. And this module DLT rho bar decomposes as a product over all the embeddings like a DLT sigma rho bar. Analog to we just saw for the tensor induction of rho bar, the module. Over this coefficient ring, so this coefficient ring also decompose in this way. And so each term here is a phi to the power F OK cross module over this ring, coefficient ring. But the problem is here, it seems that you get some modules with the OK cross action. But the difference is that if you look at the variable here, so each variable, when you look at the OK cross action, when you look at the action of TK sigma, you still get some elements inside this one. Somehow it's a single variable. But when you look at the multivariable ring A, here we have variables yi. It really gets something involving all the variable yi. Yeah, it's not a single variable action. So it's hard to compare these two actions of OK cross. And to compare the two actions, we pass through some perfection. So there is a morphism from left-hand side is Fyi 1 over P infinity. You take join all the P power units, P power roots of Yi. 2 on the right-hand side is Ftk sigma. Also take a perfection. So K cross acting on the left-hand side, you let P acting like a P. So P plus P with that. And on the right-hand side, on each variable tk sigma, you have an action of k cross. Okay, so you have action of k cross f. So here you need a little bit different that you have a phi f action corresponding to the action of a p. I mean on the right-hand side. You also have the action of SF. So SF is a permutation group. Okay, it translates all the variables. Okay. So this morphism denoted by M, it identifies left-hand side with some delta semi-product SF invariance of right-hand side. So here delta is the kernel of this multiplication map. So for an element here, you have A0, A1, until AF minus 1, you take product here. And delta is the kernel of this map. So SF will acting on this delta. You then have a semi-product here. So on the right-hand side, when you take delta times SF invariance, you will get induced action of K cross. Because when you mod by this subgroup, you get K cross. And M is compatible with these two actions. So this is a way to compare the action on the both sides. You need to pass through perfection. So a little bit more precise, how to decide the image of M on each yi. It is determined by this some formal identity. This identity is taken inside this weight rings of the right-hand side. Invert P. Okay. I need to go to here. Yeah. Well, I need some B plus, right? Okay. Yeah. Well, I didn't precise it. You need to you can find some related things in the work of Frag and Fontaine to to see that you can you develop a right-hand side, you can write it in this form, and you can determine. So this means Tesch-Müller lifting, and mod P you can get the image of MYI and determine this. So next we let A infinity to be the completion of the perfection of A. To simplify the notation, I denote by U sigma to be the open subset of the adic space of F tk sigma 1 over P infinity for each sigma. Okay. Then you have such a diagram. So here you have product U sigma inside here. So here we take all sigma. Okay. And the map M here will induce a map on the adic space Z. So the adic space of A infinity is a subset of that one, and you take inverse image here. An important proposition result of a Frag says that M inverse of adic space A infinity is a pro-adal delta semi-product SF tosser over this spot A infinity. And now we pass through the construction of dA tensor. So we start with this Galois representation rho bar of dimension arbitrary. Okay. Then we first have the Lubin-Tate phi OK cross module. I mean, for each sigma, we have such a phi F OK cross module. We first pass through the perfection. This 1 over infinity here. So it corresponds to some vector bundle on this product space. We denote it by V rho bar sigma. And now you restrict to the subspace M in M inverse spa A infinity. So you first have some equivalent vector bundle here, then you restricted it here. And because M is a tridial torsor, you can descend to spa A infinity. So next step is you descend to some vector bundle on spa adic space of A infinity, and the action is part of the induced action of K cross. Then you take global section, you will get back some etale phi OK cross module over this A infinity. And this part you use some result of Ketlaya and Liu. Now you descend again to get an etale phi OK cross module over the ring A, which you want. Okay. The dimension of this module is, or the rank of this module is the dimension of rho bar to the power F. Okay. When this dimension is 2, you get a rank 2 to the power F, as we computed for dA of pi rho bar. And then, then the main result of this of the talk, is that we have an isomorphism between dA of pi rho bar and dA tensor rho bar, like we indicate in the introduction. You have the diagram commute. Okay. For the proof, I also explained how to compute the left-hand side. So for the right-hand side, you can compute for general n. And for the isomorphism, we only find our way that we write down explicitly both sides, and you compare. You find it coincide. Okay, it's not a conceptual proof. Just you compute both sides, and they coincide. Okay. So we only did the case semi-simple because it's a lot of computation and a lot of combinatorics. And later on, a student of Christophe Breuil, Yitong Wang, he treated the non-semi-simple case, roughly following the same strategy, but still more involved computations. And so I will stop here. Thank you for your listening.
Are there any questions for Professor Hu? Okay, if not, let's thank Professor Hu.
Thank you.